Hey guys, welcome back for another chemistry lesson. Here, we're going to talk about the 3 different methods for calculating some thermodynamics calculations. So there are 3 different ways to do the same calculation to get the same answer. Basically, to figure out how much energy gained or lost is associated with a particular reaction. The first method for how to do this is bond enthalpies. So we are going to use the enthalpy associated with a given bond to sort of figure out the energy of the entire reaction, because we're going to do it with all the bonds. Right? So in this reaction, we have methane, gas, and oxygen reacting in a combustion reaction to give us carbon dioxide and water. Right? So we have these carbon-hydrogen bonds. We break them, and the amount of energy associated with that bond is absorbed to break the bond, right? So it just so happens that we have 4 of those bonds, so it's going to happen 4 times. We're going to do the same exact thing for our oxygen-oxygen double bonds, and I have 2 molecules, so we're going to do it twice. So, the total amount of energy absorbed by the bonds that got broken was 2,644 kilojoules per mole. Right? We're going to do the exact same thing for our products, carbon dioxide and water, and we will add those together to get our total. And this is a negative, it's on the wrong line, my bad, but negative 3,450 kilojoules per mole released when these bonds are formed. So we have this formula if we are going to be using bond enthalpies. We take the 2,644 kilojoules per mole absorbed by our bonds being broken. That is our delta H for our bonds broken, plus the delta H for our bonds that are formed. That's that negative 3,450, so reactants and products, and get a total of negative 806 kilojoules per mole, which is the net energy released, and it's released because it's negative, when we account for both the bonds that are broken and the bonds that are formed. So that negative value that we have right here means that this is an exothermic process. So that is the first way, by looking at the energy associated with each bond in our products and reactants. The next way that we can do this is by looking at what we call the enthalpy of formation, which is the energy associated with the creation of each of the substances in our reaction. So, same exact reaction with these energies associated with the formation. Anything in its elemental form we're going to have as 0, and then all of these others have their enthalpy of formation. So the equation here is we have the enthalpy of formation for each of these substances times how many of them we have. This is our stoichiometric coefficient, which we're just pulling from here. So I have 395 for my CO2, and then 2 times my water to give me negative 877.1 kilojoules per mole. That's from our products. Likewise, I'm going to take the amount from my methane and 2 times, in this case 0, but 2 times the oxygen, and we're going to do the same thing and get our amount for our reactants. Then add those together, well, math those together, I should say. Subtract them. We're mathing them together to get our total of negative 802.3 kilojoules per mole, which is the net energy released when accounting for our products and our reactants. Notice it is very similar to the previous number that we got, which was negative 806. It's not exactly the same though. So you should expect to get slightly different numbers for every single one of these methods. Then the final method is what we call Hess's law, where we look at a collection of equations that we are given to consider for a reaction and rearranging them to get the reaction that we want, basically. All right, so this is what a question using Hess's law will look like. Right? I've got the same exact equation, and then I've got 3 reactions with their associated enthalpy changes here. Now, you'll see that I have carbon here. I have no carbon in my equation that I'm trying to get. Likewise, I have hydrogens down in these bottom equations, but don't have it up in the equation that I'm trying to get to. We're going to deal with these in a bit. Okay, so the first thing that I'm going to pay attention to is the arrow, right? The arrow is kind of our division line. We want to make sure by the end of all of our manipulations that we have the correct substances in the correct numbers on the correct side of our equations, right? So first things first, let's look at methane, right? In my final equation, I need to have 1 methane molecule on the left-hand side of the arrow. Currently, I have 1 methane molecule, but it's on the right-hand side of the arrow in the reaction down here at the bottom. So let's look at that. I need to be able to flip what side of the arrow that CH4 is on. So I'm going to do my little flippy-do in order to do that. So when I do that, flip it around, boop. What that does, anytime I flip a reaction, as you saw here, I have dropped or changed the sign. So this was a negative 74.8. Now, because I have flipped that reaction, it is now a positive 74.8. All right, so we're going to bring that back over here. And now I've got my methane molecules on the correct side of the reaction where I want it. Next, let's look at our water molecules. All right, so as we saw in the previous slide, I have water molecules on the correct side of the reaction where I want them to be. However, I need 2 of them, and in the reaction that I have, I only have 1. So we're just going to multiply everything by 2, which means that I'm going to get a 2 here, because I have 1 and I'm multiplying 1 by 2. I have half an oxygen. If I multiply that by 2, that gives me 2 halves or 1, so it cancels out the coefficient. And I currently have 1 water molecule, so 1 times 2 gives me 2 water molecules. And whatever math I do with my equation, I also have to do it to the enthalpy. So that negative 241.8 becomes negative 483.6 kilojoules. All right, so let's bring that back over here. Now that we have our water and our methane fixed, so water's good. Now let's look at the other things that we have considered. So again, methane was good. We just fixed the water. Now let's look at our oxygen and our CO2s. All right, I need 2 oxygens on the left-hand side of the arrow. I already have 2 oxygens on the left-hand side of the arrow. So they're good. Likewise, I need 1 carbon dioxide on the right-hand side of the arrow. I have 1 carbon dioxide on the right-hand side of the arrow. So we're good. Now, let's look at the things that I don't need. Remember at the beginning we talked about how we've got carbon in these reactions and hydrogens, and we don't need them because our final reaction up here at the top doesn't have carbon or hydrogen. Let's see if we've fixed the problem. All right, here I have one carbon on the left-hand side of my arrow, one carbon on the right-hand side of my arrow. They're going to cancel each other out. Then I had my 2 hydrogens on the left-hand side of the arrow, 2 hydrogens on the right-hand side of the arrow. They cancel each other out. Great. Now I don't have to deal with either of those. So what I'm left with is, if I take it in and erase that, this. All right, so I have 1 methane, 2 oxygens, 1 carbon dioxide, and 2 waters. So, as is, these things, I have exactly what I need. So what I'm going to do is, I'm going to take these 3 numbers that have been adjusted for the fact that I needed double of that second reaction, and I flipped that third reaction, and I'm going to take those numbers and add them together to get my total amount of energy that is released. So if you recall, we had our previous numbers were, let's see, I had negative 802.3, so this was exactly the same as using the enthalpy of formation, and then was just slightly different from using the bond enthalpies, which gave us negative 806. So you can do it all 3 ways to get approximately the same number, and this is how we figure out the amount of energy associated with a reaction using data that we already have, as opposed to collecting that data in a lab setting.